Hey guys, welcome to the last lecture for the semester. We're going to talk about agricultural, aviation, lunar dust, and extravehicular activity today for this one. So it's kind of a three-fer. So again, this is one that I had to kind of push things together and added the EVA stuff in just so I can get a little bit more content in for you guys. So we're going to start off with agricultural aviation toxicity hazards. So aerial application, this is what it's technically called now. It used to be called crop dusting because back when this originally started, they used this dust to dust the crops. Now it's more of an emulsified type of toxic substance, and so now they call it aerial application instead of crop dusting. So just from a terminology standpoint, basically it just describes the use of aircraft to deliver economic poisons, plant protection products, and then you can pretty much use anything to deliver this stuff. So it can be a fixed wing, airplane, rotary wing, which is another name for helicopter, and then there's some cases where you can use drones to deliver these pesticides. Just from a terminology standpoint, an economic poison is it's a mixture of substances that prevents, destroys, repels, mitigates insects, rodents, nematodes, etc., etc. So your classic pesticide, herbicide, fungicide, and it's typically primarily delivered by an airplane versus the other options we'll talk about. So the most common types, so probably the most common use for this aerial application is to distribute pesticide. So when you see an aerial applicator, I'll probably call it crop dust, I still call it crop dusting, so I'm not going to be totally correct when I say all this, but when you see a crop duster at work, they're typically delivering pesticides, so whether that's an herbicide, an insecticide, or a fungicide. You can also use it to seed fields, which is kind of cool. You can distribute fertilizer, and then kind of in another category, you can, over forests and stuff, you can administer defoliants, plant regulators, desiccants, pheromones. Fire suppression is a big one. We got kind of a cool video in here of a huge 747 doing fire control stuff. And then in some cases, you can use it for mosquito control. So it's been done, especially in like South America, in Texas, when viruses like Zika and West Nile virus are prevalent. Then these aerial applicators can deliver mosquito control agents over those areas to try to depopulate the area with mosquitoes. So this is what I originally mentioned. Originally these pesticides were given in powdered form, which is the origin of the term crop duster. So now it's a liquefied emulsifiable concentrate. And so to be technically correct, you'd say aerial application, but no one's going to smack you if you say crop dusting either. It's a big business, the art of aerial application. In the United States right now, there's 1,560-ish registered businesses for aerial application. And those 1,560 businesses use about 6,500 aircraft. So it's a pretty considerable number of businesses that are out there doing this. 100% of fire retardants that are delivered via aircraft. And then about 20% of chemicals that are applied to farmland are given via aircraft. So this is actually one. This is an S2 tracker that took this in Topeka last year. So they use these old decommissioned World War II Korean military aircraft, basically, typically to deliver fire suppression stuff. So this was doing a water bombing demonstration, which is pretty cool to see. The question comes up sometimes, well, why not just use tractors? Why do you use airplanes? It doesn't seem as efficient. But in reality, using an aircraft to deliver these pesticides or fertilizers or seeds, it's actually more efficient from a time perspective anyway. It's a really fast delivery process. It gives you access to remote areas where you may have difficulty getting a tractor into. Reduces soil compaction. So in times where, especially if it's wet, you don't want to get a big heavy tractor in there and putting these huge divots and ruts into the fields. And so using an airplane to deliver this stuff, it just makes total sense. It's actually a really quick method of getting done. A little history. The first known aerial application happened in 1906. Sort of this guy, John Chater, he basically took a hot air balloon, tethered it, and then used it to deliver seed in swampy areas in New Zealand. And then the first use of an airplane happened in 1921. Lieutenant John McCready used this. It was actually this aircraft here. It's a JN-6 Super Jenny, so it was a World War I fighter plane. I mean, it's not too sleek looking, but it was what the Americans used in World War I. Or really more for forward observation, but it's kind of beside the point. Anyway, McCready used this, distributed lead arsenate over catalpa trees in Ohio. Basically trying to control the catalpa sphinx moth larvae. They held these moths that were destroying these catalpa trees, and so McCready took his Jenny out and dropped lead arsenate over everything to kill these sphinx moths. And then the next year, in 1922, they used same aircraft to dust fields in Louisiana to control boll weevils that were repopulating the cotton fields down there. The first commercial application, so the first business that was started in 1925 by Huff and Dalen Duster Incorporated. And it's kind of a fun fact, these guys actually went on to form Delta Airlines after this. So Delta had its origins in crop dusting back in the day. And then the first use of an aircraft for firefighting purposes happened in 1930. This was the Ford Trimotor aircraft that was used, and it dropped just a simple load of water that was packaged up into a wooden beer keg. It drops on top of a forest fire. So you had the origins pre-World War II. It wasn't super prevalent yet, but then post-World War II, the business really boomed. So this was a time where you had manufacturing processes were really ramped up, trying to control or meet the need for aircraft in World War II. Once the war ended, you had this huge surplus of airplanes, and not really used for crop dusting or anything. But I mean, you could buy a P-51 for about $7,000 after World War II. That same P-51 today is worth over $2.5 million. So it was a really cool time to be able to get in and buy this surplus military aircraft. And that's actually what they did for crop dusting, is they bought all these old, especially military trainers, and reconfigured them into crop dusters. So this picture here, this is a PT-17 Stearman that was modified for crop dusting. So on the bottom here, you can see the spray nozzles. One big modification was the PT-17, or the Stearman biplane. It was a trainer biplane, and it was an open cockpit. So there were no roll bars over it or anything. To reconfigure it for crop dusting, they strengthened the fuselage. They added this roll bar here, and basically just protected the pilot. Because when you're doing this, you're flying at a really, really low altitude. I mean, your wheels are touching the top of the grass, basically. And so it's relatively easy to crash. And so if that happens, you want as much protection for the pilot as possible. And so adding this roll cage really went a long way doing that. So anyway, post-World War II, you get this huge boom that happens because there's cheap, easy access to aircraft that are ideally suited for delivering pesticides and seeds and fertilizers. Then in the 1960s, so about 15 years after the end of World War II, you started seeing the production of purpose-built aircraft for crop dusting. These became larger, they had more reliable engines, which is a huge thing. If you're flying a single engine plane, a couple inches off the ground at a time, if you have engine failure, you're in for a world of hurt. And so it became imperative to build better aircraft that had better engines on it. The pilots knew would be reliable, that it's not going to conk out on them when they're in the middle of a maneuver. And they also added on wire cutters. So actually, if you notice here, it's not uncommon at all to see crop dusters flying underneath power lines and phone lines. And you can't, if you're flying, it's almost impossible to see wires, because your rate of movement, the thinness of the wires, you can't see them when you're in the air. And so they add the wire cutters on, which there's not one on this one here, but it's, if you see the front of a helicopter, that big bar that sticks out, that's a wire cutter. And so it just increases the safety margin if you accidentally find yourself flying into a set of wires. Now, there are several aeromedical concerns that go hand in hand with aeromedical or with aerial application. So one is low altitude operation. I mentioned that you're flying, feet to inches off of the top of the crop, so you're basically dragging the ground when you're flying. It gives you much less room for error. It's very easy to make a mistake, to have a lapse in judgment, and we'll talk about some of the substances that are applied can impair judgment pretty easily. Repetitive acceleration is required for maneuvering. So when they drop in, they come in, and then you have to pull up, reverse course, come back in. You're pulling high G. It's a high G maneuver every time you turn around at the end of the field. And so to do this over and over and over for 6 to 8 hours per day, it can add up physiologically. Long duration flight days, again, that goes hand in hand with that. Mechanical and engine failures, I'd mentioned, so you want maximum reliability out of these things so you don't find yourself in a situation you just can't get out of. Engine failure tends to be one of the biggest causes of pilot deaths just across general aviation. And so maximizing that reliability becomes a huge factor for these guys. Object collision, so you see here, and actually just went out to my in-laws' farm for Thanksgiving, and windmills are absolutely everywhere on the way out there. So the whole way I was thinking was like, how are these crop dusters getting in there to do this stuff? Because you talk about massive obstacles, because they still farm around these things. And so in order to get an airplane in there, deliver your load, and get out of there safely, it adds a huge risk to the whole process. So object collision is a big issue. Not only windmills, towers that get brought up or they get put up, wires, houses, trees, things that pop up seemingly out of nowhere, becomes a huge risk for these guys. Heat stress and fatigue, it's not a nice, cool, air-conditioned, easygoing job. It's hot. It demands a lot of mental acuity. It's easy to get physically and mentally fatigued, especially with these long duration days that they're doing. And then finally, exposure to toxic chemicals, and this is a big thing. You're using organochlorides, organophosphates, parathion, malathion, things that are not really known to react well with human physiology. And so if and when pilots get exposed to this, it can decrease their ability to fly the aircraft, which dramatically increases the likelihood of a crash. Additionally, you start seeing cases where they have to do aerial application at night. So during the daytime, especially out in the farmlands, it tends to get really, really windy. It can make it difficult to A, control the aircraft, but B, it increases the risk of pesticide drift. So if you've got a 30, 40 mile an hour crosswind and you're trying to deliver this pesticide, that wind's going to blow it quite a bit. The wind doesn't blow as much as at night, and so in some cases these aerial applicators are having to fly their routes at night. That brings a new set of dangers that you have to be aware of. Obstacle impact is a huge one. So, again, going back to the windmills here, there's a light at the top of the windmill to let pilots know, there's an obstacle there. There's not lights at the bottom of the windmill, which is actually where these guys are going to be flying. There's not lights at the tip of each blade. So, you'll see if you've driven by these windmill farms at night, you can see, the lights flashing, but that's just basically a solitary light at the top of that control box there. So it increases the risk of danger. Rural electrification, so you have all these high tension power lines that are around, and it's one thing to see the power lines during the daytime, which is really hard to do, but you're basically not going to see them at nighttime. So you have to have a well laid out map of where everything is. You have to have excellent ability to fly the aircraft, and you have to have situational awareness like nothing else. Large farm equipment, so if someone, if a farmer's out in the tractor in his field and it breaks down out there and he has to leave it, then the crop duster comes in at night, again, you're flying at the level of the grass, and if there's a tractor there, you're potentially going to hit it. So that opens up a new set of obstacles. Wind farms, and then You see these METs that get erected pretty quickly, these meteorologic evaluation towers. So, there's these, couple 100 feet tall towers that get erected pretty quickly. They have the guy wires that keep it in place that increases the risk of pilots running into this stuff. So there's a lot of concern, with just terrain impact and obstacle impact, but then you also have the concerns that are related to the pesticides that you're delivering to. And with regard to that, you have the potential for the inadvertent misapplication of chemicals. So I've mentioned the wind plays a big part of this, where if you're delivering your spray load and the wind's really high, then that can cause chemical drift. It doesn't hit where it's supposed to. Pilots can miscalculate where they're supposed to be dropping the stuff. They could drop it over the wrong field. They could drop it over populated areas. That doesn't happen as commonly, but wind and chemical drift tend to be the most common things. And that's also why you see pilots fly so unbelievably low when they're delivering this stuff. And there's the omnipresent risk to livestock, pets, and to humans. So if you're spraying a field and there's cows in the field, there shouldn't be cows in the field that's being sprayed, but cows have been known to escape before. Same thing with pets, running off into the fields. Humans, I've been guilty of this, of stopping to watch a crop duster just because I can't help myself. I know you really shouldn't do that just because it can cause a distraction for the pilots. They don't know what you're doing there. If you're with the FAA trying to grade them on everything they're doing. But then, more than anything, there's the risk of chemical drift that can happen. So if you're in the wrong place and it's drifting, then you can be exposed to whatever pesticides that they're spraying. All right, with regard to aircraft that can be used, so I mentioned in the 1960s, you started to see an increase in purpose-built aircraft for this. This is probably the most commonly used aerial application aircraft. It's a sky tractor, which makes sense, tractor of the sky. It's, most of these have turboprop engines, and remember, you can tell a turboprop, it's got these huge exhaust outlets. The center of gravity, or the center of weight, is moved way forward, so it's got a really long nose to try to balance everything out. But more than anything, it's got this enclosed, super rigid, super strong cockpit for the pilot. So if and when something does happen and they have a mishap, then the pilot's going to be very well protected. And then you'd see the wire cutter here. So if they get through, the prop's probably going to cut the wires, but anything that gets through is going to be snapped right there. So it'll protect the pilot from, obviously we don't want them decapitated. So this will prevent that from happening. Aircraft that are purpose-built for this purpose are single seat and fixed wing. So single seat, fixed wing, not a rotary wing. Rotary wing is going to be a helicopter. You also see biplanes that are purpose-built for this. Those are called ag cats, or agricultural cats. You can see modified multi-engine aircraft. These are typically used for fire suppression more so than crop dusting, and then helicopters can also be used. And then 99% of aerial applicators, they'll use GPS to help guide their product delivery. For firefighting and mosquito control, you tend to see these multi-engine aircraft. They tend to be decommissioned military aircraft. So again, this is it was called an S-2 tracker. So it's a surveillance airplane that was used more so in like the Korean War. It was used in Vietnam, but they don't fly them actively anymore. It was used by the Navy. Decommissioned, so a lot of fire suppression companies or firebombing companies bought these and turned them into fire bombers, and they worked really well for that. So multi-engine, it gives you more reliability. If one engine fails, then you've still got another one that's good to go. And that's the thing with when you're flying into smoke in a fire, like a smoky, fiery area, you want as much redundancy as possible. So a multi-engine aircraft, the other thing is that multi-engine aircraft typically allow for a larger capacity. And so if you're talking about firebombing, you want to shove as much fire retardant or water as you can into these things. And so multi-engine aircraft tends to give you a little bit more cargo space for that. It also offers multiple crew members, which takes a little bit of the pressure off of pilots in this case. So if you have multiple crew members, you've got more redundancy built in, and that's coupled with the redundancy of multiple engines. Maneuverability is a little bit compromised with these. You know, they're not as agile as single-engine aircraft are for the most part, but they can operate at a higher altitude, so it gives you a built-in safety factor there. And with firebomber aircraft, you're not really as worried about getting them low to the ground to deliver the payload. It's okay if water or fire retardant drifts a little bit. It's not going to hurt anybody. It's not like you're delivering highly toxic pesticides where you have to be down at the at ground level to deliver this stuff. So these aircraft they sacrifice maneuverability but can operate at a higher altitude and higher speeds in some cases, which tends to be well suited for the purpose of fighting forest fires and firebombing. Speaking of firebombing, it's just a few seconds I'm going to show. So this is a modified 747 that they use for aerial firefighting, which is just the coolest thing. So they're still flying pretty low, but the amount of capacity they can deliver is just absolutely unbelievable. That's all I want to show you guys, is that first part of that. Just so cool watching these 747s do this stuff. There we go. So fixed-wing aircraft are primarily used, they're the most commonly used aircraft to deliver the stuff. You do see some helicopters used occasionally. Helicopters, they give you fantastic maneuverability and visibility. I mean, you can stop on a dime, you can turn, you can go pretty much anywhere with these things. The big issue that you run into, though, is the payload capacity is very low. It's a lot less than it is with aircraft, and it costs a lot more to operate a helicopter versus an airplane. So you see them in cases where maybe a little bit more difficult to access areas. So areas with steep terrain, things like that, you can get a helicopter in there a little bit easier. But for the most part, for aerial application, you tend to see fixed-wing aircraft used. It's also possible to use UAVs, so unmanned aerial vehicles or drones. They've been used in Japan actually since the 1970s, which is kind of hard to fathom when you think about it, since drones have just really now come into prominence. But you know, the military especially has used drones for a long time, since the 50s and 60s actually. But they've been used in Japan since the 70s for the purpose of aerial application. They're a good option really for very small fields. So in cases where you have a lot of obstructions that are present, so it makes it hard to get an aircraft in there, or if you have really sharply sloping terrain that it would be even difficult for a helicopter to get to, UAVs may offer a potential option. It's really not a good solution for most fields in the United States because they're so big. You know, a UAV, even a larger UAV, the payload capacity is, I mean, it's very, very, very tiny. So it takes a long time to cover any significant amount of area. So really they're only good for these niche applications where you have a small amount of area to cover and it's really difficult to access otherwise. Located on steep terrain, you just can't get another type of aircraft in there. In the United States, the primary areas where UAVs are used are in like apple orchards or you know, orchards in general, just for smaller areas, but otherwise you're seeing aircraft used for aerial application. So I've said it a few times, most application happens at very, very low altitude. It gives you maximum delivery of chemical payload, so pretty much every bit that you're dropping out of there is covering where it's supposed to, and then it minimizes drift or overspray. Now obviously the problem with this is that when you're flying a couple of feet off of the ground, you have to have maximum situational awareness. SA is absolutely paramount. The pilot has to, I mean, they're doing several things simultaneously. They have to make sure that they're applying the appropriate amount of aerial application, they're being vigilant for obstructions. When they reach the end of the line, they have to turn off the spray, immediately gain altitude, avoid any obstructions that are there, so trees, towers, cows. Quickly pitch up, then reverse course, come back through, align with the next row. They have to level off, descend, avoid obstacles, reactivate the spray at exactly the right time, and all this is happening pretty much simultaneously. So it requires maximum attention, maximum situational awareness, because there's danger absolutely everywhere. And this happens for hours and hours at a time. I mean, yes, they do take intermittent breaks, so I mean, a spray load is only going to last for so long, so they can typically make, depending on the size of the field, 5 to 7, 10 passes. And they'll have to fly back to base, refill their tanks, and then come back. But typically, that's a quick turnaround. They may stop and take bathroom breaks from time to time, but we'll talk about in a little bit that a lot of pilots prefer not to. So this can add an increased level of risk to the operation, which again we'll talk about. There's several risks for impairment that we have to be aware of. So any condition at all that impairs the pilot's ability to make quick judgment and react quickly can be deadly for the pilot. So yes, there's always the risk of sudden incapacitation. So if the pilot has a sudden heart attack, which has happened before to pilots, it's a risk, but it's not really as common. Pilots in this role tend to be healthier than the baseline population. And so the overall prevalence of a sudden incapacitating event, so stroke, MI, something like that, tends to be pretty low. The more common issues that you run into are fatigue. So again, these are long duty days, it's hot, and this happens during the summertime. There's a lot of G loading that goes into this. It makes pilots tired. And when you get tired, you don't think as clearly, and if you don't think as clearly, then you make mistakes. Distractions, so you're coming in, you're focused on your spray line, but then there's always things going on inside the cockpit, outside the cockpit, so it can be easy to get distracted. And if you get distracted, again, your situational awareness lapses and it puts you at increased risk. Medication-induced impairment, this is typically due to sedating antihistamines. So working in this line, I mean, you're exposed to a lot of potential allergens, and it's not uncommon for some sort of allergies to be popping to happen here. And so if a pilot takes Benadryl or other sedating antihistamines, then obviously that dips into your situational awareness and it puts you at increased risk. And then finally, toxin exposure, which is a really big one. I mean, you're flying with this huge tank of pesticides. You have to fill the tank, which increases the risk of exposure. You have to apply it. Wind can cause it to come back into the cockpit if it's not done right. When you're cleaning the airplane, you're exposed to this stuff. And it's not like once you're exposed, it's just a quick effect and then it's off again. This can have residual effects, which can definitely impair the ability to fly like you're supposed to. There's a risk of acceleration. So you have these repetitive G loads that are being induced. The goal of aerial application is to minimize the amount of terrain you're flying over. So you deliver your spray load, you want to get turned back around as quickly as possible, come back in, deliver your next line, which means that to do that, you're having to pull these really tight G maneuvers to get back on line again. And if you're doing this over and over and over, then that impairs your ability to withstand these G forces for a constant period of time. Now, most pilots are able to tolerate G load, but there's conditions that can decrease your overall G tolerance. And if your G tolerance decreases, it makes you fatigued a lot more quickly. And we've talked about the role of fatigue in situational awareness. But it can also cause blackout. So if you pull too many Gs, you black out, you're this close to the ground. That's not going to end well. There's factors that can decrease your overall G tolerance. One of them is elective dehydration. So I mentioned a couple slides ago, a lot of pilots don't like to stop to take bathroom breaks. It interrupts their flow. It takes longer to get the job done. Pilots want to get in, they want to get the stuff done, they want to go fly. They don't want to waste time on the ground going back into the bathroom. And so you'll see very much not recommended, but a lot of pilots will electively dehydrate themselves, meaning they want fluid load. They, in summertime, hot, your mom always said, make sure you drink enough water, drink enough Gatorade. In some cases, they aren't doing that here because they don't want to use the bathroom. That's kind of like when we're talking about physiologic changes to astronauts. A lot of astronauts will electively dehydrate themselves prior to launch because they don't want to be sitting in the in the rocket, having to go to the bathroom right before liftoff. They don't want to use the diapers. In this case, these pilots aren't wearing diapers, but they don't want to stop, land, go to the bathroom, come back, start it all up again. And so elective dehydration increases or decreases the G tolerance, which increases the risks to the pilot. Same thing for heat loading. They're doing these long duty days during 100-degree weather sometimes. It can overheat them pretty quickly, and as you overheat, as your core body temperature increases, your ability to withstand G's also decreases. And then finally, hunger. If you're in the cockpit and you're hangry, then it decreases your ability to focus. So, or decreases your ability to focus, but it also, you're nutritionally depleted, which again, physiologically makes you less able to withstand G's. Now, just as an example of how these guys operate. So this was up in Liberty. I was there I was coaching my son's baseball team, and there's a big field next door, so they're doing crop dusting, so of course I had to park in a remote place and go watch them, but they're at a crop level. So then a little push-pull to get over that road. And he does it in this case, but you can see all these wires over here. He was flying under the wires earlier, but it's immediate pitch up, roll, trying to reverse course. So in that type of maneuver right there, you're probably pulling at least 2.5 G's, and then you come back in. So if you weigh 200 pounds, then that means you feel like you weigh 400 to 500 pounds in the cockpit. It's a hard pull, over and over and over all day long. Can really take a toll on the body, and so it's a very dangerous job. So I mentioned push-pull when he popped up over the road and pushed back down. So push-pull can decrease your G tolerance. So when you push the stick forward, nose goes down, that induces negative G's. So everything rushes up, but then immediately you pull, pushes everything back down again, you have positive G's. So if you're doing obstacle avoidance, so if you, coming up over the road, so you pull, you have to push to get back down again, and you have to pull to level out. So it's that repetitive push, pull, negative, positive G's over a prolonged period of time really decreases your G tolerance overall. Antihypertensives are a big thing. So if a pilot's on an antihypertensive, especially something like an alpha blocker, it can increases the risk of orthostatic hypotension, we know, but it decreases the ability to, oh goodness gracious, I can't think of my words now, like reactive vasoconstriction. So it decreases the ability to react to these sudden pressure changes. And overall, the end resultant effect is it decreases cerebral perfusion pressure and decreases cerebral blood flow, which increases the risk of bad things happening in that case. And then exposure to organophosphates is going to be a big thing that decreases your, in addition to everything else, will also decrease your G tolerance. As far as chemical exposure goes, there are 1.8 billion people in the world that are involved with agricultural pesticide delivery, handle pesticides on a routine basis. But out of those 1.8 billion, those who are aerial applicators that handle these pesticides and toxins on a routine basis are actually the greatest risk out of all agricultural disciplines combined. There's over 1,300 pesticides registered with the EPA. There's actually more pesticides that are out there under different branded names, but there's about 1,300 that are registered with the EPA. 6 billion pounds of pesticides are used worldwide, and herbicides account for about 60% of that usage. There's the current trend in farming is to minimize tillage in order to reduce fuel use, soil erosion, and to decrease compaction. So compaction, again, being run a tractor over something that compacts the soil, makes it harder to penetrate in through there. And so there's more of a focus on decreasing all this stuff, which means that the use of aerial application is expected to continue increasing over time. Agricultural pilots are going to be exposed to hundreds of pesticides throughout their career. One really interesting thing is that studies have really shown little to no increase in cancer risk among aerial applicators. Although there's thought to be some sort of bias with this, where you're looking at kind of a healthy worker effect, where people that are involved in aerial application tend to be a lot healthier than the baseline population. So to be a pilot, to get your license, to have your medical certificate, you have to be in good health overall. And so when you look overall at this group of pilots versus general population, the group of pilots is going to be healthier at baseline. So it makes sense that their all-cause mortality is decreased overall versus the rest of the population, just because they're healthier at baseline. As far as pesticide exposure goes, so this is an AgCat, as I mentioned, so a biplane purpose-built for aerial application. Pilots can be exposed to pesticides when they're being mixed, when they're being loaded into the aircraft, like it is right here, when they're applying it. So if there's any breakage in seals, or there's something happening with the tank, there's some kind of a draft into the cockpit, it can pull the pesticides in. They can be exposed at that point in time. And then also when the aircraft is being cleaned, they're at higher risk of exposure. The issue that you see here is that pesticides are easily and readily absorbed through the dermal barrier. So they can be absorbed quickly through the skin and also through vapor inhalation. So two primary means of exposure to these pesticides. The ones that are primarily in use, chlorinated hydrocarbons, organophosphates aren't used as much anymore, but they're highly, highly toxic. Carbamates and pyrethrins and pyrethroids. Pyrethrin is it's a plant-derived toxin, so it's generally less toxic than other pesticides. So there's more of a trend towards this group, but you still may see some organophosphates that are used from time to time. Organophosphates are the most hazardous group, and we'll go through the mechanism, but they that should not have an apostrophe there. I'm kind of a grammar Nazi. So yeah, should be just blocks. Ignore the apostrophe. I don't know how I got in there. It blocks acetylcholinesterase, which leads to unabated cholinergic neuromuscular activity, which can be absolutely deadly. All right, so at baseline, what happens? So you have your acetylcholine molecule right here, and it gets attracted to acetylcholinesterase through this electrostatic attraction. So it binds to this anionic site and the esteric site. Once it binds to acetylcholinesterase, it gets cleaved, and so it breaks into acetic acid and choline. And this happens in milliseconds. So about 20 milliseconds after introduction of acetylcholine into the body, acetylcholinesterase attacks it and breaks it down. So it's a very, very quick process. Now, if a pilot or anyone is exposed to organophosphates, then basically what happens, this is your organophosphate, so we're going to call it a pesticide. They're also used as nerve agents, which is why this says this here. But so you have your organochloride, your OC or your OP pesticide gets attracted to this acetylcholinesterase, and it gets more so attracted to the serine component. The organophosphate attaches to the acetylcholinesterase. It blocks it up. It loves the serine, so it forms a really tight bond there. It loves it. It doesn't want to let it go. It's going to stay there. So it binds up this acetylcholinesterase, which takes it out of circulation. Basically, it makes it not available to break down acetylcholine. So cholinesterase is now blocked. So your organophosphates come in. It's bound. It's blocked up this cholinesterase. So there's one of three things that can happen. So it can hydrolyze to its original state. So if this bond hydrolyzes, and it can break it off, which is a very slow process. You can regenerate the acetylcholinesterase with an oxime, so like pralidoxime, something like that. Or this bond can age, which means that it gets stuck there and it cannot regenerate, it cannot hydrolyze. It 100% takes that acetylcholinesterase out of circulation. Each different agent has a different aging time. So basically, In order to reactivate or to replenish this acetylcholinesterase, you have to get it hydrolyzed or regenerated before it's able to age. And each agent has a specific aging time that's associated with it. We're not going to cover all those. That's for a different class, a different lecture, but just know that it has to be treated before it ages, otherwise it's completely gone, which takes it completely out of commission. If that happens, then, so pilots, in this case, that are exposed to it they can experience their cholinergic toxidrome. So you have your classic sludge, muscarinic symptoms of salivation, lacrimation, urination, diarrhea, GI discomfort, and emesis. Or dumbbells is another mnemonic that's used. So diarrhea, urination, meiosis. So remember meiosis, your pupils get tiny. Mydriasis is where they get big. So M in this case, meiosis or muscle weakness. Bronchorrhea, bradycardia, emesis, lacrimation, and salivation. You can also experience nicotinic symptoms. So your muscarinic receptors have to do with kind of the wetness that's going on in the body. And then you have your nicotinic symptoms, which can cause, or if you remember the days of the week, so muscle cramps, tachycardia, weakness, twitching, and fasciculations. So these nicotinic symptoms tend to be more muscular symptoms. So on the, I was about to say muscarinic right after that, and then I had to stop thinking what I said first. So nicotinic symptoms tend to be more muscular in origin. Muscarinic symptoms tend to be the wetting effects. So these kind of drag everything down, make everything really wet. And then if nicotinic symptoms kicked in, then you get, potential seizures, muscle cramps, weakness overall. Basically, if you look at these, you imagine yourself flying high G maneuvers at very low altitude and you're experiencing any of these symptoms, it's not a recipe for success at all. So again, it becomes a very dangerous proposition to be exposed to these organophosphates. So what can you do if you're exposed to it? One, we had talked about administering or regenerating the acetylcholinesterase, and so you can use pralidoxime, which is also known as 2-PAM. So if this is administered before that bond ages, then you can regenerate the acetylcholinesterase and you can fix it. Atropine, so on the muscarinic side of things, it causes bradycardia, pretty severe bradycardia. So early on when they're exposed to this, you will see patients be very bradycardic, and so in order to reverse that, you give the antimuscarinic atropine. So it won't correct the nicotinic side, it doesn't correct the muscular side of things, so it won't do anything if they're having the muscle twitching, if they become paralyzed over time, which again, you don't really tend to see in the pilot side of things. This is more of a higher level exposure. Pilots do experience the muscarinic symptoms for sure. And if they do, atropine is going to be what will fix that. But it can take huge amounts of atropine to fix these. A normal dose of atropine, so if you have someone that comes in with symptomatic bradycardia, we'll give 1 milligram of atropine, half milligram to 1 milligram of atropine. Which should fix baseline symptomatic bradycardia. If someone's exposed to an organophosphate or organochloride, it can take hundreds of milligrams of atropine to reverse the effects of what's going on. So it can take huge amounts for this to happen. And then pyridostigmine, pyridostigmine is a cholinesterase inhibitor. Which, so organochlorides and organophosphates. So why would pyridostigmine help in this case? Well, basically what it does is it's a reversible acetylcholinesterase inhibitor. So it binds up with acetylcholinesterase. It prevents the organophosphates, organochlorides from binding to it. And so if they can't bind to it, then they get processed through the body normally. Then the pyridostigmine dissociates and the acetylcholinesterase is back in action again. So this is just kind of a way of inhibiting, preventing the acetylcholinesterase from being aged by the toxin. So it's just used as a prophylactic agent. So with all this being said, atropine is the big way to fix the muscarinic symptoms that happen after this pesticide exposure. An unfortunate thing is that some pilots have been known to self-treat with atropine, so they'll either prospectively treat themselves or they'll just treat themselves kind of as they see fit, which I don't know how they're getting a hold of atropine, but it's been shown all over the place that some pilots will self-treat with atropine when they're spraying the fields. This is not a good idea at all. Worst case scenario, you give yourself atropine, you don't get exposed to any of the pesticides, and now you're severely tachycardic. It's an antimuscarinic, so it dries up all these secretions, so now you get super dry, and it's going to change your focus in another way, and it's going to increase you, it's going to open you up to danger again. So it's absolutely not recommended to self-treat and prophylactically treat with atropine in this case whatsoever. Otherwise, you can find yourself in accident. So agricultural pilots, they're exposed to hazards that just can't be eliminated. You can't eliminate all the windmills. You can't eliminate the obstacles completely. There's always going to be something coming up that's going to increase the risk of danger. There's a death rate of about 1 per 100,000 flying hours, which is 3 times higher than pilots in any other aviation industry. So it's the most deadly aviation profession. And the majority of crashes are due to engine failure. So even though, I mentioned from the 60s on, they tried increasing the reliability of engines never work with 100% efficiency, with 100% reliability. There's always the risk of engine failure. A lot of it depends on your maintenance crew, how well things are being kept up, but there's always that risk. There's the risk of loss of control, whether it's due to control surfaces breaking, whether it's due to loss of focus. There's any number of things that can happen. And then collisions with things. And then more recently, low-level drone operations have increased the risk. So, even a small drone, if an aircraft hits it, sucks it into, hits the engine and causes engine failure immediately. So that's the equivalent of like a bird strike, which can be deadly too. 62% of accidents with aerial application happen during the maneuvering process. So in that video I showed you, he pitches up, pulls, banks, comes through. 60% of the time, accidents are going to happen during that time. When you're in that high degree of a turn, so you're at about 60 plus degrees of bank coming through there, it decreases the airflow over the wings, increases the risk of stall, you have to maintain a decent amount of airspeed to compensate for the reduction of lift. If you don't, so if you have engine failure in that configuration, you're going to stall and you're going to crash. The good news is, though, that with these purpose-built aircraft, you can see this one's pretty torn up, but look how intact that cockpit is. So the pilot probably got hurt to some degree in here, but walked away from it. That cockpit is in remarkably good shape compared to how the rest of the airplane looks. Some of the case reports that have come out, so there was an experienced pilot who spilled parathion on his clothes while he's pouring concentrate from a 55-gallon drum. He's got this big drum trying to reconstitute the stuff. Gets it all over his clothes, doesn't really do anything about it. 4 days later, starts having these effects of just, like severe irritability, introversion, these neurologic, psychologic effects. Not psychologic, but he's having psychosocial changes that are going on. Had a bad headache, wasn't feeling well, and ended up crashing his plane. And this was due to the changes induced by the parathion that he spilled all over himself and didn't immediately decontaminate himself. Another pilot was exposed to drifting parathion, required atropine therapy, ended up crashing into a tree during pull-up. There was another case where a pilot was flying on takeoff. The connection between the tank and the sprayer broke, and it sprayed parathion into the pilot's face while he was flying. So that should say saturating. I'm blaming this on autocorrect. It didn't suture his body, it saturated his body, which caused him to lose control and crash. And then another case, another similar type of instance where The pilot was splashed with defoliant during a flight, which caused a crash. So this inadvertent exposure due to lines breaking, seals breaking, spills, things like that, play a huge factor in overall pilot safety with this. So this brings us to the end of aerial application. So summarize, there's a ton of dangers that are involved with aerial application, especially with pesticide exposure. So next up, we're going to talk about toxicities of lunar dust. We're completely switching gears here. Okay, so the lunar surface, the land and the sea. So this just kind of give you guys a little bit of baseline of terminology that surrounds the moon, different areas of the moon. So you guys probably noticed if you look at the moon, the bullet-shaped thing that shoots everything out, it's called Tycho crater. You don't really need to know that, but anyway, there are two primary surfaces of the moon. So first you have the Maria, which is the plural, or mare. So in this case, like mare imbrium, mare serenitatis, mare tranquillitatis. This is Latin. Mare is Latin for seas. So the early astronomers actually mistook these darker areas of the moon for seas. They thought it was actual water on the moon, and so they called them the Latin for seas. These are formed by ancient asteroid impacts on the far side of the moon that end up triggering volcanic eruption on the near side of the moon that produced this very iron-rich soil regolith that gives it this darker appearance. So it's the iron-rich composition, iron oxides that give it this darker look on the surface of the moon. The majority of Maria are on the near side of the moon. There's actually very few on the far side. And actually, if SLS launched the Orion or Artemis 1 mission. Orion is the capsule. Right now, Orion is it's in a retrograde orbit. It's on the back side of the moon. It's taken some amazing pictures of the far side of the moon. So actually, if you go and look at those, you'll see that there are very, very few of these darker Maria that are present on the backside. They're relatively flat. They're basaltic areas. So when you look at the moon and you see the dark side, those are the Marias. Then you have the highlands, which are the lighter areas. This is primarily the crust of the moon. They're anorthositic. So anorthosite, it's an intrusive igneous rock that's very calcium rich. So it's the lighter areas of the moon. These are also known as terrae, which is Latin for land. So you have the land and the seas, the terrae and the Maria. It's the heavily cratered and rough areas of the moon. Now, lunar dust. So lunar dust is actually a very toxic, very complicated substance that's on the presence of the moon that has been a rate limiting factor for us setting up a permanent outpost on the moon. In order to establish any type of either permanent or even semi-permanent presence on the moon, we have to figure out how to manage lunar dust. It's a component of regolith. So regolith is the lunar soil, basically. So, if they say the lunar regolith, they're talking about the lunar soil, and then the dust is a component of that regolith. It's formed by micrometeoroid impacts. So you have these hypervelocity micrometeoroids that kind of just pound the surface of the moon. There's no atmosphere on the moon, and so, these things are hitting with massive, massive speed. And when they collide, when the micrometeoroids collide with the moon, it gets superheated. It creates this glassy, jagged edge, glutenate. It is very sharp and likes to adhere to a lot of things. And then over time, they keep getting pulverized by these micrometeoroids into super, super fine dust. So the texture of the soil overall, it evolves. It's not consistent. It's not static necessarily. But it changes due to reworking by the micrometeoroids. But overall, it's a very fine particulate matter that leads to, again, these sharp-looking agglutinates that tends to adhere to most surfaces that it comes in contact with. So it mentioned that it's been said that the rate limiting factor for our presence on the moon is the problem of dust. And one of the issues that you run into, this is actually a proposal for a new landing system for the moon. So as of right now, when you go to land on the moon, it kicks up all this dust. So this dust is like a very fine powdered, almost like graphite. It's like ash, basically. So if you barbecue something, you go out on the grill, you pull off a handful of ash, that's almost what this dust is like, except it's sharper, it's more adhesive, it gets absolutely everywhere. So if you try to land in the middle of that, it's going to kick dust up absolutely everywhere. And it can extend for tens to hundreds of kilometers. So you can imagine if you're trying to land a lander on the surface of the moon, and you have your habitat not too far away, it's going to absolutely cover that in dust. It's going to interfere with electronics. It's going to have a lot of problems associated with that. So actually something that's interesting, this company, it's trying to create a new landing system called FAST, which is an in-flight aluminum spray technique. So basically what it is, it's this company called Maston, and what they do is when they fire these retro rockets to bring it in for landing, they're going to inject ceramic particles into the rocket engine nozzle. And this builds up a coating over the regolith, so it injects the ceramic, and then it starts coating the regolith with a ceramic, which then starts to build up, and they start to adhere with each other, and then it creates a hard landing pad that has a lot better thermal and ablative resistance. So if it works, it can significantly reduce deep cratering, because every time you land, you're creating a crater. It can prevent regolith and dust ejection, so it decreases this problem, which basically overall means that a spacecraft could land safely on the moon pretty much anywhere without the need to build a landing pad in advance. Because ultimately that could be the solution, is to build a landing pad on the moon in order you can land on it and not kick up dust. But the problem is, it becomes a chicken and the egg thing. Like, how do you land on the moon to build this without landing on the moon? Because it has to be built before you can land, kind of thing. So this, if it works, could be a pretty innovative solution to decreasing the dust problem and increasing our ability to return with greater frequency to the moon. Just as a real-life example, this is the Apollo 17 lunar module. So they landed on the moon, and then this is the ascent stage right here. So just to show you how much of a problem this dust can be, this is a video of the ascent stage igniting here. So this is Gene Cernan and I think it was Jack Schmitt. So Jack Schmitt and Gene Cernan in Apollo 17 lifting back off again.
Port, take your arm to that. Okay, I'm going to get the pro. 99, proceeded, 3, 2, 1, ignition.
So you can see all this dust getting kicked up there.
Ag start.
So it's still one of the coolest videos ever. So basically they had the lunar rover that was parked like 150 meters off to the side of the lunar module. And so they had a camera set up right there. And the camera's actually controlled from Houston by one of the mission controllers. And so we had the timing just right to catch that descent stage going up. But you can see it again. Just watch the dust that kicks up.
2, 1, ignition. Burn away, Houston.
It's a lot of dust. All the shiny color things, that's foil that was getting kicked off of the lunar module. Anyway, so dust is a huge issue with takeoff and with landing on the moon. It's like trying to land in the middle of a pile of ash. It's stuff that's going to go absolutely everywhere. And this dust, it has electrostatic forces that cause it to adhere to anything it touches, especially spacesuits. So this is Jack Schmitt's spacesuits. I mean, look how dirty that is. So then you get these agglutinates that get in there, and they're very sharp. They adhere to everything. When they adhere like this through these electrostatic forces, and you come back into the lunar module, you're bringing all that dust back in with you. And as soon as you get back into the environment, then it just kind of, well, on the moon, you have reduced gravity. It's not microgravity, but that dust still gets everywhere. So it can interfere with your instrumentation. It covers all that stuff. It can foul atmosphere. So you have all this dust that's floating around in there. It gets hard to see through that. So, again, just as an example, if you go to the barbecue grill and start pounding the ash and all that comes up and try to see through that, it's not going to happen. And then that dust goes absolutely everywhere. So it interferes with vision. It can get into the eyes, which is going to irritate the eyes really badly, which it did on almost every mission to the moon. It can cause respiratory distress. This particulate matter is very small, and anything less than 30 microns is pretty easily inhaled. And so it can get down into the lungs pretty easily. And then it leads to dermal irritation too. When you just look at the shape of the dust, it can abrade pretty easily, and so it can cause a lot of dermal irritation. This is Gene Cernan. So again, Apollo 17, and his suit was absolutely covered too. But you just look at how much is on his face, on his forehead, everywhere. The stuff gets everywhere. So I mentioned vision obscuration. So all this dust starts coming up into the habitable area, makes it harder to see. You inhale it. It's a very significant respiratory irritant. It's allergenic. That has triggered a lot of allergic response on these Apollo lunar missions. It's very abrasive, so it would actually cut the spacesuits in places. It would cause a lot of dermal abrasion too. It gets into the instrumentation, and it can cause false instrument readings. You can get a dust coating everywhere that gets contaminated. It's not as much of an issue. So if you're on the moon, because you still have 1/6 gravity, you still have a little bit of gravity at play there. It's not going to be free floating necessarily, but as soon as you get back up to the command service module, or you dock and get ready to come back home when you're in absolute microgravity or 0 Gs, then that dust just picks up and it floats around everywhere, and it can contaminate everything it comes in contact with. In high enough concentrations, it can lead to loss of traction. So on the moon, you're trying to walk from point A to point B in your habitat or in your lunar module or wherever you are. Increased risk of fall. Granted, it's not significant, but it's still there, especially if you're trying to carry equipment from point A to point B. That can clog mechanisms, leads to thermal control problems. So if you have a thermal control surface and it gets covered with dust, then it loses the ability to control that temperature like it should. And then it can get into the seals of spacesuits, and it can lead to seal failures. It's a very abrasive material, and so once it gets in there and it starts rubbing after every extravehicular activity with all this movement, it can start to break down the seals. And if the seals of your spacesuit fail, then that's not going to be a good thing at all. So this is a significant hazard that poses a huge risk to astronauts. All right, so a little bit more on regolith. It's 10 to 20% of the lunar soil is fine dust with particle diameters of less than 20 microns. And 1 to 2% is, and so these less than 20 microns can still be inhaled, but the very fine, less than 3 micron size, gets all the way down into the alveoli. And so with enough concentration there, it can lead to severe respiratory distress. It can lead to hypoxia, which you don't obviously want to have happen when you're on this surface. It resides in a near vacuum environment, the regolith does in general, and it's constantly subjected to radiation. So there's no atmosphere on the moon again, so you have ultraviolet light coming from the sun that's irradiating the soil. You have X-rays that are being given off from the sun, from other stars, and then also gamma radiation that's coming in. So it continues to irradiate the soil over and over, and this happens during the daytime. Then at nighttime, it's subject to solar winds. So again, just all these sources of radiation and can make it hyper excited and irradiate this stuff. So this irradiation imparts a positive and a negative charge to the soil, which means that this dust is going to contain unsatisfied chemical bonds, which are going to make it hyper reactive. So it makes it very reactive, which also increases the ability for it to adhere to anything it touches. It's trying to satisfy those chemical bonds, which is part of why it sticks to absolutely everything. So it'll foul up everything very, very quickly. The regolith itself has minerals from anorthositic, which again is a type of igneous rock that's very calcium rich, gabbroic, and basaltic type of rocks. The minerals that make up the majority of the regolith are aluminosilicate, ferromagnesian silicate minerals. So there's a lot of like silicates and sharp things that make up the regolith. 80% of the fine dust itself is a silica-rich glass. So a very classy composition, which we know glass is very abrasive, so it makes sense that the fine dust that composes the regolith is also going to be very abrasive. I don't know why that happened. That increases the risk of toxicity to the astronauts. The more that they're exposed to it, the more that they inhale, the more pulmonary irritation, discomfort, distress that it can cause. These are some quotes from astronauts that have actually had the ability to walk on the moon, just kind of describing how prevalent of an issue it is. So one says, I think this might have been Cernan, so after liftoff, when we were again in a zero-G environment, a great quantity of dust floated free in the cabin. This made breathing without a helmet very difficult. Enough particles are present in the cabin atmosphere to affect our vision. Rocks, so this is talking about extravehicular activity on the surface of the moon. Rocks were present under the surface of the dust, so it's easy to trip and fall. The surface isn't uniform. Lunar dust is like ground down lead. It's similar to the grindings in a pencil sharpener. It's very tenacious and made zippers very sticky. Now, if you think about sticky zippers, that becomes a problematic situation. So if your zipper is sticking in the lunar atmosphere, each time you zip and unzip, it increases the tension on the zipper and it increases the likelihood of it breaking. And a broken zipper on the moon is not going to be a good thing. Another one says, we're quite dirty from our legs to our knees, from our hands to our elbows. It's like we had been working in powdered graphite, which seemed to cling to us. Concerned that once we got back in orbit, we wouldn't be able to remove our helmets because of the dust floating in zero-G. We dusted ourselves, but there was dust everywhere. It smelled like gunpowder, which is an interesting side note that pretty much universally all astronauts describe the smell of lunar dust as smelling like gunpowder. Versus with astronauts that do spacewalks, so they do EVAs in space, they say that space has kind of a raspberryish, ketonish type of smell, apparently. So they smell it on the suits when they come back in. But the moon smells like gunpowder. But you get desensitized to that smell. The suits would have to be doffed before entering the vehicle. So we were saying that they'd have to fully get out of their suits before they get back fully into the vehicle. Otherwise, they're going to track all this dust back in. Dirt is soft like powdered snow, but it clung to absolutely everything. Suit, cabin, hardware, skin, everything else. Another said it was so dirty you couldn't see the maps on the extravehicular activity. Lunar dust was ubiquitous during the lunar surface activities. And then so much dust was on the camera, they couldn't get the filters on and off. So they had a polarigraphic filter they're trying to get on, but so much dust had accumulated in the connections there, they couldn't get that filter on. Jack Schmitt, so again, probably the award for the dirtiest astronaut to come back goes to Jack Schmitt. If I remember right, he was a geologist and had a really hard time standing up on the surface of the moon and kept falling. So his suit got absolutely filthy. And as part of this, he had a really severe allergic reaction to the dust. So like really bad hay fever type of symptoms, had to use a lot of nasal decongestants, but he went on to say that dust is the #1 environmental problem on the moon. So we have to understand what the effects are, because there's always the possibility that engineering might fail. So you can create engineering fixes to try to get around the problem of dust. The problem is dust is ubiquitous. It's always going to be there, and it's going to find the point of failure with our engineering solutions, which means that we have to have contingencies upon contingencies to try to plan for all this, because dust is going to find a way. So there was actually, in addition to Jack Schmitt on Apollo 17, there was severe respiratory tract irritation noted on Apollo 12 and Apollo 16 in addition to 17. So Apollo 12 was Pete Conrad, Dick Gordon, and then Alan Bean. Apollo 16 was John Young, Charlie Duke, and Kent Mattingly. And then 17 was Cernan, Ronald Evans, and then Jack Schmitt, which Ronald Evans was the command service, or he's the CSM pilot. All right, so back in, I believe it was 2005, they established this group called the Lunar Airborne Dust Toxicity Assessment Group, also known as LADTAG for short. And what their job was to quantify how toxic the lunar regolith is. So what toxicities are we expecting to see when we go back to the moon? How can we plan for this type of stuff? So again, established in 2005, the goal was to set the starting point estimate for the range of safe exposures. So they're looking at 6 months of episodic safe exposure. So how much could they be exposed to over the 6-month period, potentially on the surface of the moon, ranging from 0.01 milligrams per cubic meter to 3 milligrams per cubic meter for respirable dust, and setting a short-term exposure limit of less than 1 hour. So the whole overall goal of this was just to set the starting point estimates. They noted that lungs do appear to perform well in microgravity, which is good. Obviously, we want things to breathe. The question is, how adherent is the dust to the pulmonary and mucosal surfaces in microgravity? And what they found is that there's actually reduced deposition in partial or microgravity. So the lungs still work, you're still able to breathe, you get good gas exchange, good oxygen exchange and transfer. But they do show that the dust doesn't deposit as well in partial or microgravity. So partial gravity being the surface of the moon, ultimately the surface of Mars. What they did find is that fine particles less than 1 micron are going to be deposited in the very deep peripheral regions of the airway. So the smaller the size of these particles, the more likely they are to be deposited. Even though deposition in general is decreased, the smaller molecules are still going to find a way to get in there. Which means that lung residence time is also going to be longer. So if it's kind of floating around there, it's going to be there for a longer amount of time, which is going to increase the rate of time that toxicologic effects can occur. They did a lot of intratracheal instillation and inhalation studies in rats. So obviously they didn't subject humans to these studies. These are all done in rats. And what they did was they took dust from Apollo 14 and they wanted to measure the amount of lung damage that happened after rats would either breathe or they would instill this dust into their lungs. And they were measuring lung inflammation, septal wall thickening, fibrosis, and the presence of granulomas. And what they found is that lunar dust has somewhat of an intermediate toxicity level. So it's higher toxicity than titanium dust is, which kind of surprisingly, titanium dust is low toxicity overall. So lunar dust is more toxic than titanium dust, but it's less toxic than quartz dust is, which kind of makes sense. Quartz is very glass-like. It's if it gets in there, it's going to be very toxic. So it's somewhere in between titanium and quartz dust. And they also found that pretty much a common sense statement, but signs and symptoms of lung damage become more severe with the dose. So the more lunar dust you inhale for a longer amount of time, you're going to see more toxicity. They found that there were no observable adverse effects, or the NOEL, so the no observable adverse effect limit, was 0.5 to 1 cubic milligram for a 6-month mission. So as long as we keep exposures to less than 0.5 to 1 milligram per cubic meter over a 6-month mission, there shouldn't be any observable adverse effects. Now, if you compare this to the OSHA, the current OSHA limits, so for earthbound work, for respirable fused silica dust, That limit is 5 milligrams. So, 5 to 10 times higher limits for OSHA as compared to what NASA will be instituting for lunar dust exposure. But again, you have to have that margin of safety that's built in. So if you're going to be on the moon for a 6-month period, you're, at minimum 3 days away from coming back home, which is pretty good. But versus, if you're on Mars, you're years from being able to come back home because you have to wait for alignment of the planets to get there and to get back, and so that'd be a different proposition. But looking at the surface of the moon for a 6-month mission to the surface, as long as you keep that exposure to less than 0.5 to 1 milligram per cubic meter, the astronauts shouldn't experience any adverse effects. Our knowledge of lunar dust is still really limited. Working with a couple samples from Apollo 14, we haven't been to the moon since 1972. There's a lot that we don't know. There's a lot more questions that have to be answered before we can start looking at establishing a permanent presence there. So one question is the overall surface reactivity of dust different than samples on Earth? The guess is yes, that the lunar sample, or that the lunar dust is going to be more reactive than samples that are on Earth, again, because samples on Earth have likely undergone some degree of chemical passivity, where the oxygen and the water, the trace amounts of water in the atmosphere will kind of denature that dust a little bit. We don't know for sure how much radiation affects lunar dust. So it's exposed to solar winds, solar flares, cosmic sources. We don't know how much more reactive that different exposure limit makes the lunar dust. We don't know if the physiochemical properties are different between dust that's studied in situ on the surface of the moon versus that which is brought back and studied here. Don't know, if an astronaut's exposed to a high level of dust in a very short period of time. Don't really know what the physiologic effects of that are going to be. We can infer that the risk of pulmonary toxicity is going to be much higher if they're exposed, and it kind of backs up with what the lab tech studied in the rats, that signs and symptoms are expected to be more severe with higher dose and longer duration exposures. So if you're exposed to a very high concentration in a very short period of time, it makes sense that you'd have some sort of reaction to that. And I also need to elucidate the role of gravity in attenuating the site of deposition of particles in the respirable range. So we know that there's a decreased deposition of particles in the lung tissue in either microgravity or reduced gravity. But the studies that have looked into that are very, very young. There haven't been many studies done into that. The body of knowledge surrounding that topic is very small. So there's a lot more to be learned in terms of the overall physiologic responses and the deposition of these particles. Anyway, the bottom line is there's a lot we don't know about lunar dust. We know it's toxic. We don't know how toxic it is. We don't know how much of a role the solar radiation plays. We know that it makes it more reactive, but how much more reactive? How much more reactive is it on the surface of the moon compared to the samples that we have here? So there's a lot of things that have to be answered before we really start looking at establishing a long-term presence on the surface of the moon. Some astronaut reported events that occurred. Lunar dust exposure was consistent throughout the Apollo program, which obviously makes sense. These guys are on the surface of the moon. We know that it's very electrostatically active. It adheres to everything it touches. But what they did find after that was that the lunar module and the command service module, so just for clarification, so when I say, so this is Apollo 11, this is the launch escape tower, which would have already been ejected, but this is the command service module. So you have the capsule and then kind of the trunk there. So this was left orbiting. There we go. Here's my moon. So the CSM, Command Service Module, orbited the moon the entire time all the astronauts were down on the surface, and then the lunar module landed on the surface of the moon. The ascent module brought the astronauts back up. They docked with the Command Service Module, got back into the CSM, put my moon back, ejected the ascent stage, and then the Command Service Module came back to Earth. The capsule detached from the trunk and then re-entered the surface of the atmosphere. So anyway, when I'm saying Command Service Module, that's what I'm talking about. So it was left orbiting the moon. So when that ascent stage came back up, docked with the CSM, astronauts came back into the CSM. It brought a lot of dust in with it, and it kind of fouled the atmosphere, made visibility decreased. It increased the amount of dust that's brought into it, basically. Apollo 14 overall had the fewest problems with lunar dust, which is interesting because that was the mission that collected all of the lunar dust samples to bring it back to Earth, but they had the fewest problems with it. All astronauts reported smelling the dust, so they all said it smelled like gunpowder. And if you smell something, it means that it's entered into your respiratory tract. You can't smell something if it's not inside your respiratory tract. So that became a consequence of inhalation. And then all astronauts reported respiratory and ocular irritation, some more so than others. Jack Schmitt, I say poor guy, he got to walk on the moon, but he had the worst go of it, so he had a pretty severe allergic reaction to this dust getting into his respiratory tract. The good news is that there haven't been any observed long-term detrimental effects as a risk of, or as a result of being exposed to lunar dust. The caveat, though, is that all of the lunar missions that NASA undertook were pretty short duration. So Apollo 11, they were there on the surface for a matter of a few hours. And then Apollo 17, they were there for, I think, 3 days, give or take. So Apollo 17 was obviously the longest duration on the surface of the moon. I think it was 118 hours. So it would have been longer than that, but or no, maybe a little bit less. Anyway, I'm sidebarring myself. The bottom line is, though, that no matter if it's 3 days, 5 days, whatever, it's a short duration on the surface of the moon. When we're looking at setting up a semi or a permanent base on the surface of the moon, I mean, you're looking at long-term duration missions, so 6-month missions at a time. So we don't really know what the effects of that duration of exposure are going to be. So we're going to have to, so if Artemis 1 is successful, comes back, brings back more information, and then Artemis 2, we actually send our first astronauts back to the surface of the moon, it's going to require setting more formal exposure limits versus the kind of brief NOAE, the NOAAs that were established by LADTAG and all those exposure limits. Those are more theoretical, so we're going to have to get more solid evidence to set more formal limits. Excuse me. All right, so what to do about this dust problem? So there were several recommendations that came from astronauts. One, and probably the top of the list, was protect the zipper suit function. They said that dust was very difficult to clear from the zipper, that after each extravehicular activity, the zipper worked less and less. So it worked perfectly the first time, and then less, because all that dust gets trapped in there. It's very abrasive. It starts to break down and wear down the surface of that metal. And again, if you have a zipper failure in the vacuum of space, it's not a good thing. That dust, it scored the metal connections, especially the bearings. So if something was rotating on a bearing, it would circumferentially start to degrade that surface, which is not a good thing. The good news is, again, from a limited exposure on the surface of the moon, the dust didn't breach the suit seal, but repeated exposures to the stuff are definitely going to increase the risk. Again, the longer term duration missions on the moon, it's going to become more and more of a problem. Next recommendation from the crews were provide airlocks for ingress and egress. So right now we'll talk about a little bit when we talk about EVAs, that they use an airlock on the space station for coming and going. So You get suited up in the airlock, then the airlock depressurizes, matches the vacuum of space. Astronaut goes out. When they come back in, door behind them closes, repressurizes, and then they can open up the door to get back into the ISS. The recommendation here would be to do essentially the same thing for lunar surface or Martian surface EVAs for that matter. So come in off the surface of the moon. For the lunar module, they would walk back up the ladder and they're immediately back in there. For subsequent missions, looking at establishing a solid airlock, coming back in, blocking that off, being able to get undressed in the airlock, and then come back in and minimize that tracking in of dust into the habitable area. They need an increased ability to clean the body and rinse eyes and nasal passages. Again, dust was everywhere in the habitable area. So every astronaut reported there was a lot of dust back in the lunar module. It was really difficult. It took days to get it cleared off of their hands from under their fingernail beds. And most of them experienced eye irritation to some degree. They kept getting this dust in their eyes, and it's that really sharp knife-looking dust. It's not pleasant. So it required a lot of irrigation with saline in order to get that out of there. So there needs to be a better way to clean the body, to clean the eyes, to clean the nose, to get rid of this dust. They are requesting better or more medications to help manage the effects of this. So nasal congestion is experienced by most astronauts. So whether on the surface of the moon or in the space station, we talked about the physiologic changes that happen. Nasal congestion is a very common issue that occurs. It becomes more of an issue when you get exposed to this dust on the lunar surface. So that, plus you're in a 100% oxygen environment, and there's the potential for viral exposures prior to flight. You need something to help clear up this nasal irritation and decrease this respiratory distress that has the potential to happen. Historically, they used Actifed, so nasal decongestant, that worked decently well. It gave them a little bit of relief, but not what they were looking for. What astronauts described was that they'd be they left the command service module, got to the surface of the moon, and this nasal congestion would get really bad. But then as they got out onto the moon, then it would decrease a little bit. But then when they got back to the command service module, this nasal congestion really hit them hard again. So finding better medications to help treat this, prevent this from happening, will increase astronaut comfort considerably. Other mitigation strategies that they're looking at, so design modification of surfaces to help decrease the electrostatic interaction between the surfaces and the dust. So basically a different form of dust repellent within the surfaces, the equipment, the instrumentation. Part of how they could do this would be exploitation of the ferromagnetic properties. So the moon surface, especially in the Maria, it's very rich in iron oxides. So if you can take advantage of these ferromagnetic properties and basically create something that repels that dust, be a good solution. Providing carbon dioxide showers at the airlocks and electrostatic curtains to help repel the dust off of the astronauts themselves. Create electrodynamic dust shields, so that kind of ties back in with exploiting the ferromagnetic properties. Finding a self-cleaning spacesuit, which would be awesome. A lot of that will probably have to do with the ferromagnetic properties again, finding a way to create a natural repellent system. Using photovoltaic electrodes to repel dust, and then electron beams to neutralize electrostatic charges. So we're getting into the more high-tech solutions here. Something that may be able to be incorporated. So this is the SpaceX's proposed Starship lunar lander. Actually, this is an interesting solution to the dust problem too. So the lunar module that were used in the Apollo missions were probably about as tall as where this landing leg is. So relatively small. The engine nozzle was down there very close to the surface. Created a lot of dust. One design feature of the Starship lunar lander is that when they're coming into land, they're not going to fire up these bottom thrusters down here to land it. They're going to actually have thrusters, control thrusters, that are ignited from towards the top of the Starship that will help it land. So that's going to decrease the amount of force that actually impacts the lunar surface, which will decrease the amount of dust that gets kicked up during landing. So it's a pretty innovative solution. The downside to that is that they have to take a big old elevator to get to the bottom of this. I mean, this is a very, very tall structure here. So they'll have to be reliant on the elevator working to get in and out of the habitable area there. But it could significantly decrease the risk of dust being kicked up. And then finally, the next major problem that arises is, we have plans to go to Mars. If dust is a problem on the lunar surface, it's 3 days away. It's going to be a major, major issue on the surface of Mars, which we're looking at multi-year missions out there. So there have been working groups to establish the approach to how to manage this, and the first thing that has to be tackled is how to filter the dust on the Martian surface. So you have to have filters that are working consistently and reliably, because dust storms are very common on the surface of Mars. You don't see dust storms on the surface of the moon. There's no wind on the moon. It doesn't kick things up. There's no storms. It's if something impacts, it's going to kick up dust, but there's no surface dust storms that just spontaneously occur. On Mars, there are. And this is going to be a huge limiting factor to our ability to go to Mars. So to go there, to build an outpost, to build a habitable area, one of the first problems that has to be fixed, solved, decided upon is how to effectively and reliably filter the dust out of the atmosphere. Traditionally HEPA filters, the high efficiency particulate air particle filters, have been used. They're used on the space station. They're used in the lunar modules, which worked to filter out the larger size dust, but it didn't do a very good job with the more respirable range size particles. Have to figure out a better solution for Mars, because the HEPA filters are going to have to filter everything. And again, it's going to have to be reliable. If they break down, then how is an astronaut going to be able to fix that on the surface of the moon when you're 8 months away at minimum, or it's actually be longer than that again with a planetary alignment trying to get back. So that's a major, major problem that's going to have to be solved before we can even consider going to the surface of Mars. Okay, so that we bring it to our third and final component, which will be extravehicular activity. So extravehicular activity, also known as EVA, I'll just call it EVAs from here on out. The process of conducting an EVA, it exposes crew, equipment in the mission it exposes them to significant risks. Tools can be damaged and lost, mission objectives can fail, astronauts can experience a wide range of injuries. They can get cuts and bruises, they can get thermal burns. So their lives, the lives of the astronauts, they depend on a long list of hardware and procedures working absolutely perfectly. And if anything goes wrong with these procedures, then the astronaut may not survive. Mishaps that happen as part of an extravehicular activity typically fall under 3 different categories. They can fall under hardware failures, hardware damage, or missteps that are taken by the astronauts or by mission control. And so overall, special considerations have to be taken to make sure that all the equipment that's used by the crew can withstand that EVA environment, and that the operations that are required of the crew, so the mission parameters that are there for the crew to complete, that they don't put the astronaut at a significantly increased and unnecessary risk. So we're going to go through, we'll talk about what EVAs are, what the dangers are that are associated with them, and then we'll talk about some of the mishaps that have actually occurred that fall under those 3 categories of hardware failures, hardware damage, and missteps that have been taken. So an EVA, it's defined as any activity performed by a pressure-suited crew member in an unpressurized or space environment. So this means spacewalks, It means walking on the surface of the moon, ultimately walking on the surface of Mars, or wherever we go. The surface of an asteroid has been talked about, which would be a really cool thing. With regard to the suits that are actually used, we'll talk a little bit more about them in depth to some degree, but in the United States we use what's called an extravehicular mobility unit, or an EMU, or an EMU. In Russia, theirs is called the Orlan. There's some subtle, some not so subtle differences between the suits themselves. I'll show you what each of them looks like and what the differences are between them. But there are two different suits that are used in space. We have ours that are used by the United States, and then by the European Space Agency, by JAXA, by other countries' agencies. And then you have the Russians that do their own thing, and they use their Orlan, which Orlan is Russian, I believe, for eagle. So you can take that for what you will. The process of an EVA generally begins with depressurization. So they get suited up, they get into the airlock. Once that airlock is depressurized, that marks the beginning of the EVA. And then the clock stops once that airlock has been repressurized at the end of it. So depressurization to repressurization is the window for the EVA. The first EVA was performed by Ed White, astronaut Ed White, on Gemini 4. This is Ed White during the Gemini 4 mission. The spacesuit that he used, or it wasn't an EMU, but the spacesuit he used was a little bit different than what current astronauts use. This happened on June 3rd of '65, and it lasted a total of 36 minutes. So a pretty short duration spacewalk. When astronauts go out and perform an EVA, they're in, well, saying it's a harsh working environment is probably an understatement. I mean, the atmosphere, the lack of atmosphere, is actively trying to kill them at every moment. There's a very thin margin for safety that goes on with an EVA. So when they're in the ISS, it's the atmosphere of the ISS is maintained at 14.7 psi. So good, working pressure. When they get into the the mobility unit, or the EMU, it's pressurized at 4.3 psi. So it's significantly lower pressure than what it is when they're on the ISS outside of their spacesuit. If that pressure in the EMU were to drop to just 2.8 psi, it would lead to a loss of vision. So they'd have a blackout. If it drops, or vision blackout, if it were to drop to 2 psi, they would lose consciousness. So it's a razor thin line between successful mission and then a catastrophic mission. It all has to do with that suit maintaining good integrity and being able to maintain that PSI they have it set at. There's three different classes of an EVA. There's the scheduled EVA, the unscheduled or an off-nominal EVA, and then contingency. And then tasks that get performed on these EVAs are classified as either being basic difficulty, moderate difficulty, or difficult. And we'll talk through what all those are. So a scheduled EVA. This is conducted to complete all the pre-planned nominal tasks that get outlined in the mission parameters. This is on a very tight scheduled timeline. Their support overall mission operations. So these are the things that are planned well before they get into space. They know exactly what they're going to do, on what timeline they're going to do it, and how it's going to happen and get done. So it's considered a nominal EVA. Now, an off-nominal EVA, these are done when something comes up that's not included in the pre-flight mission parameters, but it's necessary to achieve mission success. So they have to, something fails and they have to go out and fix it. Something needs enhanced while they're up there. They hadn't planned on doing it, but they're up there, so we're going to go ahead and get it done. These are things that weren't planned, but they have to do them anyway. These are considered off-nominal EVAs. Then you have contingency EVAs, which is another type of off-nominal, but this is a lot more dangerous. So this is done when something has to be done to affect either the crew or the vehicle safety. and it's done to ensure that the vehicle and the crew are able to return safely to Earth. So in this case, this is a contingency EVA that happened not too long ago, 2009. So Scott Parazynski, he was on the, so this is him, he's mounted to the Canadarm, or the mounted robotic arm on the space station. And he had to go fix this tear that happened in the space station's solar arrays. So this is a very dangerous activity that had to happen, but this is something that had to be done right away in order to maintain structural integrity of the space station, the safety, the continued operation of the space station, and to ensure that crew could return safely. So this contingency EVA is something that has to be done, otherwise it's going to affect the overall outcome of the mission. As far as tasks that get completed on these EVAs, so there are, again, basic, moderately difficult, and then difficult tasks. The basic tasks are the ones that they just use standard tools, standard restraints or mobility aids. Something that's easy to do, basically you're flipping a switch, you're rotating a dial, you're doing visual inspections. You don't need special training to go out and do this, any special training beyond actually how to perform an EVA in general. But there's no special skills that weren't trained in, that they didn't train in prior to the EVA occurring. It's something that doesn't require much coordination between the crew members, so between the inside and the outside. The success of the mission isn't contingent on continued communication and cooperation. It's something that's a very simple visual inspection, again, flipping a switch, something like that. And then the work sites are easily accessible. So it's not on a remote section of the space station. It's something that's easy to access. It's in sunlight. It's easy to see. Again, something that's easy to complete. Moderately difficult tasks, on the other hand, they require additional equipment, but they're still generally procedurally simple. It may take a skill set that's not used frequently. It's not unique, but it's not used frequently. So it's something that may be a little bit out of practice in. It's something that's just a little bit more difficult than the basic task, is the easy way to say it. It does require some cooperation and communication between crew members. You may have to improvise and modify existing procedures to make it done. And importantly, more extensive training is needed to complete these tasks versus the basic tasks. And then the difficult tasks, these require a notable extension of capabilities. So you may have to use specialized tools, mobility aids. It presents a significant issue for access or restraint problems. So again, translating to the backside of the space station in a dimly lit area that's difficult to access, working on the solar arrays. These are going to be difficult tasks because they're hard to get to. Remaining secured to the station itself becomes more difficult. It requires very unique skills. So a great example of this is when they had to repair the Hubble. None of the astronauts had trained to rebuild a telescope before. So these were all skills that had to be learned above and beyond, well above and beyond what they had trained for initially. It's difficult to access the Hubble. Required the robotic arm, or the Canadarm is what they call it, to get there. Required intricate maneuvers to get to the Hubble itself, to get the service panels open, to actually get in, replace the hardware, correct the aberrations with the focusing equipment that was going on. Requires time-critical, very intense coordination between crew members. So this is something that requires a lot of synchronization of tasks, of communication. You have to trust who you're working with because they have to do things at exactly the right time so you can do things at exactly the right time. It also requires the use of the remote manipulator system operator. So the astronaut that's attached to the Canadarm, they're not controlling it. There's another astronaut inside the station that actually controls that arm. And so they're very reliant on that system operator doing things, I don't say make sound bad, but they are completely reliant on that system operator. So again, that cooperation, the collaboration between crew members becomes paramount. This is the most hazardous classification, so there's the greatest risk of injury, of death to the astronauts, especially when you get to working on solar arrays, and we'll talk about the risk of forming molten metal and shock and everything that can go with this. So the difficult tasks, these are obviously the ones that are the most dangerous. They require the most coordination, communication, training, learning of new skills that they didn't think they would ever need before to make the mission successful. Okay, we mentioned the EMU, so this is kind of a breakdown of all the components of the EMU. It's basically a miniature spacecraft, if you think about it like that. It provides environmental protection, mobility, life support, communications equipment. The suit itself, so the American solution to the spacewalk suit, it's a little bit convoluted. It takes at least 2 people to get dressed. So you can't just jump into the suit. You have to have someone to help you. So if, for whatever catastrophic reason, there's only one person on the space station, they wouldn't be able to do an EVA because they would likely not be able to get dressed on their own at this. So there's a lot of different components. So you have your liquid cooling, ventilation, undergarment, your disposable bags, your helmet with your communications equipment, your helmet. You have to get these multi-piece arm assemblies on with the gloves that are notoriously difficult to get on. It's a very tight fit into the suit. It's really hard to get into the torso section of it. It requires a lot of contortion. It's described as not being pleasant at all, especially if you're claustrophobic. But it can take over 30 minutes to actually get dressed in the EMU. There's a lot of components that go into it. The suit itself, it's designed for a maximum mission duration of 7 hours. This includes 15 minutes for egress. So when you're getting into the suit, getting everything turned on, pressurized, your clock starts. 15 minutes of ingress, of getting back into the airlock, a 6-hour mission duration, and then 30-minute reserve time. So they don't do any missions greater than 6 hours because they have to maintain this 30-minute reserve time for consumables, so for oxygen, for fluids, things like that. So your mission's kind of capped out at 6 hours on site performing activities, which is still a really, really long time. But again, overall, 7-hour total mission duration, absolute maximum, and that's counting the 30-minute reserve time that you have. So on the left side over here, this is the Russian Orlan. So there's pros and cons to each, but probably the biggest pro side to the Russian solution is that it doesn't take multiple people to get dressed in it. Basically, you open up the backpack here, and then the cosmonaut jumps in that way, and then they can close themselves up inside of the suit. So it's actually pretty quick. It takes about 5 minutes or so to get into the Orlan versus about the 30 minutes plus 2 astronauts that it takes to get into the EMU. So anyway, 2 sides of a different coin, 2 different solutions. Again, each has pros and cons, but not one is not better than the other. I guess I'll put it that way. All right, when an astronaut is on an EVA, if they're unrestrained, which means that they're going to be tethered to the space station. They're going to have their umbilical and they're going to have their tether. So it's not like they're free floating necessarily. But when they're unrestrained, meaning they're not secured into something on the side of the space station, it means that they're limited to very low force, very short duration operations. So they're limited to flipping switches, turning dials and toggles, doing visual inspections and things like that. You can exert slight impulse loads by holding onto the structure with one arm and then, turning dial or, manipulating something with the other arm. If you think about it, it's the equivalent of if you go into a swimming pool and you're going to the deep end and you're floating kind of in the middle of the pool and you think about trying to do any significant actions in there. You can't do it because there's no forces being exerted from opposing directions in order to provide the torque that you need to get things done. So in a swimming pool, you can go in, you can flip some switches, you can turn some dials pretty easily. But if it comes to actually trying to use torque to get something secured or to unscrew something, it's not going to work out very well because you're just going to rotate around what you're trying to do. So these unrestrained EVAs, you're pretty limited in the actions you can take. So again, flipping switches, doing visual inspections, you don't need to be restrained to do that. Now some of the tethers that they use, so just kind of here for your reference. So there's, if they use a rigid tether or a body restraint tether, so this keeps them, it gives them a little bit more secured connection to the site. So it allows for better degree of two-handed tasks, and it gives them greater control versus a free-floating astronaut. So if you're free-floating in space, it's hard to maneuver yourself, it's hard to manipulate things, but if you have a rigid tether that's keeping you connected, so it doesn't give a lot of flex or bend, keeps you kind of secured with where you are, you get a little bit more strength that you can work with in order to complete your tasks. Now to take it up a level, they can use foot restraints. So the use of a foot restraint, it allows for a very high load to be adapted. So it allows them to do the same type of work that they could do in what's called a shirt sleeve environment. So it provides a resistive force. It uses Newton's third law of opposite but equal reaction. So if they're secured into the foot restraint, you can just imagine it. You can provide more torque. Now, with that being said, you can apply more torque within a relatively small area. So there's typically a 16-inch diameter cylinder that they can work within and use maximum strength. As they move up in this envelope, up into like this 26-inch cylinder, then the amount of strength that you can apply starts to decrease. Because it increases the lever arm with this, it increases the load distribution, which comes into play because sorry, I lost my train of thought. It comes into play because the higher that you get, it distributes that load a little bit more. And on the space station, they're going to be attached to these load alleviators that protect the structure of the space station itself from these high induced loads, which means that if you apply too much torque from too high, it translates that energy down, and it can actually rotate. It can rotate the footrest down there, so you start to lose strength the higher up that you go. So for optimal delivery of torque and strength, you have to stay within that 16-inch cylinder, basically directly in front of your body right there. Now, once astronauts are in their EMU, they experience a degree of sensory degradation, which is kind of inescapable. When you're outside of the habitable environment, you're at an increased risk of being hit by something that's floating in space. So micrometeoroids, space debris, things like that. So these suits have to be pretty thick and pretty strong if they were to be impacted by a micrometeoroid, to help deflect some of that energy and protect the astronaut inside. And so overall, it leads to a decrease in tactile sensation. They can't feel, you don't have good feel of anything. You're inside of this really thick suit, so your tactile sensation starts to degrade. You also have pretty significant decrease in visibility just because of the visor construction. So the visor size is limited just by physics more than anything else. There's no peripheral vision inside of this, so you're pretty limited. You have horse blinders on essentially. So in order to see next to you, you have to physically rotate the suit left and right to be able to see. And then in space, we talked about Rayleigh scattering in the atmosphere, and that's how everything gets brightened up on the surface of the Earth. In space, there's no light scattering, and so anything that sun impacts is going to be exceedingly bright, and anything that the sun doesn't hit is going to be very dark. So there's this division between light and dark that's very intense, which means that anything that's in the shadowed area of the space station is going to be very hard to see in an already degraded visual range of, or in an already degraded range of vision, field of view. So it's going to be even tougher to handle in that shaded area. Especially if with this decrease in vision, your tools are attached by a tether. Here in that, you have about 3 feet of play in that tether. And so if that tool floats out, you may not be able to see it, which means you could impact it, it could cause damage to the suit, you could impact the space station because you can't see directly out of the side, which you go back to those very difficult tasks, or the difficult tasks that you're doing. If you're in a hard to reach area with structural components there, your field of vision is so limited, it's easy to bump into things that are on either side or even behind you. So this sensory degradation becomes a big problem in space. It doesn't allow you to perform with your full faculties, essentially. Alright, so in space, it's very difficult to maneuver. That's one thing Ed White learned on that initial spacewalk, is that trying to control your body in space, it's almost impossible. So the ability to pitch and roll in space, the ability to do that is minimal at best. It's really hard to adjust your body in that way. Roll is easier than pitch a little bit, but only if there's a rail that's available to hold on to. Yaw is really the only direction the astronaut has any manageable degree of control over. On top of that, stopping is very difficult, or at least stopping with any precision is very difficult, even under optimal conditions. So now if you're trying to carry weight or carry a load in space, so let's say it's easy to translate from position A to position B in space regardless of how much weight you're actually carrying, because in space there is no weight, so that becomes a non-issue necessarily, the act of translating. What does become an issue, though, is getting yourself stopped if you're carrying this extra mass. Inertia is a real problem. So things that are in motion tend to have a tendency to remain in motion unless acted on externally. So if you're carrying something that has a significant amount of mass, it's going to take a significant amount of stopping force to stop that mass, which means that you're going to crash through something. You'd be able to carry something that on Earth would weigh 700 pounds, but trying to get that mass stopped in space is very, very difficult. So the ability to maneuver while weightless is difficult. The ability to transition with weight is very difficult. It's just not an easy environment to work in. The jetpack looking thing that they're wearing right here. So this is another safety mechanism for if an astronaut is they're on an EVA and they had a tether failure or something that kicked them off of the side of the station, they have this safer thing here that helps protect them. So it's got thrusters that are built into it that can help them return to the space station so they don't get cast off into space. Because if you get separated from the space station and you don't have this thing on and you're not tethered, then there's absolutely no way for you to get back in unless there was another EVA that came out to rescue you. But if you're out there on your own and you get detethered, even if you're floating pretty much right next to it, you cannot get back. There's no atmosphere to work in. You're in a vacuum, so you're limited to any external force that's acting on you. You can't, even again, trying to translate your body position, trying to roll or pitch, you can't do it. You can change your yaw to a degree, but you can't roll or pitch, which means that you're not going to be able to get back to the space station. So this is a huge safety development, or I've been talking for too long, I can't think of my words. So anyway, all this put together weighs about 700 pounds. So you have 700 pounds of mass, 700 pounds of inertia or inertial activity. So it's very, very hard to get stopped on an EVA. The gloves tend to be very restrictive also. They're similar to a balloon when they're inflated. They've got a very significant resistive force. So they're about as stiff as an inflated football is. So if you're having to if you're doing these repeated operations with your hands where you have to open and clench consistently, or screw something in, grasp, or any fine motor control, the hands are going to exhaust very quickly because it's a really difficult force to work against. But the gloves have to be thick because that's going to be the first potential point of failure on the spacesuit. These are some pictures of what it looks like. So the hand actually goes in, and then it goes into the arm. So it just kind of doesn't look very comfortable, but that's what it looks like. It's a point of fatigue for the astronauts, depending on how much manipulation. That, combined with the fact that you have pretty much no tactile feedback. It's all blind activity, so it's like putting on a pair of mittens and trying to do fine motor control. That's very, very difficult with this. It really opens up the door for crew fatigue. EVAs, they're physically demanding, they're mentally demanding. Situational awareness, just like our crop duster pilots or aerial applicators, have to maintain impeccable situational awareness the entire time, which is very mentally draining. So obviously, the longer duration a mission is, the more fatigue that's going to be present. And also any repetitive movements. So they're in a pressure suit, so 4.8 psi is inside of the suit, so repeated arm movements, hand movements, manipulations. It takes strength to fight against that force. So the more that you have to do that, the more fatigue will come into it, especially if you're on a 6-hour EVA. There's a significant amount of fatigue that'll come in with that. One way to overcome this is to minimize the use of threaded fasteners that require repeated fine motor control and manipulation to get them screwed in, to insert or remove them. Minimizing any continuous torque applications, minimizing extended gripping functions are all ways to help protect the astronaut's health and their strength on an EVA. Another danger is just the environment itself. I mentioned that you're in a vacuum that's trying to kill you at every turn. And the thermal environment is very harsh. So this is one thing that may be overlooked from time to time is, we know space is cold, but it's cold in the shadows. If you're in sunlight, it's actually exceedingly hot. So the safe thermal temperature range on an EVA would range between minus 180 degrees Fahrenheit up to 300 degrees Fahrenheit. Anything that's on the sunny side of the space station, if you touch that, it's going to be exceptionally hot. Astronauts have been burned on EVAs before just from that thermal exposure from the sunlight itself. But if you get into the shadows, then it's exceedingly cold. So there's really no happy medium. It's either like boiling hot or it's almost absolute zero. And then the hardware that's out there exposed to this vacuum, it gets continually exposed to heat and cold in a cyclic fashion. So it can degrade the equipment very quickly. It has to be very robust to handle this type of environment, but it increases the likelihood of something breaking that's going to force an EVA to go out and fix it. Now, the most common EVA hazards are associated with the suit. I'd already mentioned the suit's considered an independent space vehicle, and any damage whatsoever could be completely life-threatening. Oops. Hazards that happen as a result of inadvertent contact are the most difficult hazards to avoid. So I mentioned the visibility is very, very limited in the EMU. So it's easy to say, I'm going to be very careful, I'm not going to make any contact with anything, but if you just physically can't see peripherally, it's hard to avoid some of this inadvertent contact sometimes. And then the light-dark contrast also makes it hard. It's like, going from a cave out to the bright sunlight and back into the cave again. It's just, there's no happy medium, no happy in between with this stuff. So it makes visibility very limited, which dramatically increases the risk of inadvertent contact with something else. And why this is important is that you can't puncture the suit. This suits can be punctured by sharp edges that are present, by any burrs that happen. So when you rub metal together or you cut metal, it creates those metal burrs on the end. It can rip the suit. Corners can rip it. NASA has the requirement that anything that goes on the space station has to have rounded metal edges, or the metal edges have to be rounded. But it doesn't always prevent sharp edges from forming. Sometimes those burrs can happen with the rubbing or with cutting and things like that. So a puncture of the suit would be potentially catastrophic. Now, both the EMU and the Orlan have reserve oxygen that can be used. So if there's a leak that lets oxygen out, they have a reserve supply that they can use. But in order for that to be effective, the puncture in the suit has to be very, very small for that reserve oxygen to have any benefit for the astronaut. Any puncture that's greater than 1/4 of an inch would be fatal. I mean, so a tiny, tiny puncture would kill the astronaut. And even something as small as just a pinhole puncture, so the slightest escape of pressure means that they're going to call the astronaut back in right away and they're going to terminate that EVA. So there's, again, a very fine margin. We're talking about fine margins with the PSI that's in the suit. There's a very narrow threshold for safety with regard to punctures in the suit also. Now, there have been multiple cases where they found cuts in the gloves, and the gloves tend to be the most common means, or the most common times that the EMU gets penetrated. So shuttle mission 72, 76, 116, in post-flight inspections, they found that there were sizable cuts in the gloves in all those missions. The one that happened in shuttle mission 76, or STS-76, basically what happened there was hardware that was going to be taken to the space station. It got through pre-flight inspection, and then they had to do some more work on it. And then after that work, it exposed a metal wire on the side of that piece of hardware. And so when it got up into space and they installed it, that wire punctured the glove, which led to EVA termination right away. So, the suits are very tough. They're very strong, but it still doesn't take that much to puncture something. And when you're working in that vacuum, so whether you're in just working off the space station, replacing hardware, repairing things on there, or you're on the surface of the moon and getting the dust in all these areas that are abrasive and continually rubbing, it's not that difficult to see a hole forming. And again, anything greater than 1/4 of an inch could be fatal to the astronaut. Chemicals are concerning. If they're exposed to any type of corrosive chemicals, it could corrode the seals within the suit, which could then lead to a leak and could kill the astronaut. It could also craze the visor. So you start to get that visor crazing. It makes it more opaque. You can't see through it. It already degrades the poor vision that you have through the helmet. So any exposure to this could be exceptionally dangerous. And something that may not be as apparent, but if something were to get on the suit and stain it, it can affect the thermal properties of the suit. So in fact, they found out one time they were looking at materials to kind of reinforce the, so there's carbon-carbon tiles on the back of the suit that help with thermal distribution and keep things within the temperature range. And what they found was that this material to reinforce that actually degraded the ability of the suit to manage these thermal properties, and so it became a lot hot. It get a lot hotter, a lot easier. So something that just even changed the color or stains the suit itself can affect the ability to control the temperature within the suit. Kind of goes without saying, anything that can adhere to the visor has the ability to affect visibility. If you get material in the gloves, it can be transferred and contaminate other hardware. So, for example, it could affect the hatch seals that could prevent the repressurization. So you get back into the airlock, you get this crap on your gloves, it can contaminate the seals. You could make it to where you couldn't repressurize that airlock. so you couldn't get back into the ISS itself. And also, it's really hard to clean the suit while you're in the vacuum of space. It's hard to clean it, and it's hard to verify it's clean. So there's always the potential that you're going to get something on you on your spacewalk, and you can bring it back into the space station. So any chemical that's used during the EVA, and this includes something as simple as a lubricant, there's extensive testing that has to be done to make sure that it's compatible with suit materials. So you can't have anything that's going to weaken the seals, that's going to stain it and degrade the thermal distribution of the suit. Everything has to be proven to be compatible before it can be introduced into the EVA environment. Any material that an astronaut could conceivably use that has the potential to cause corrosion enough to where it could breach the pressure barrier, the visor, the helmet, has to be contained with 3 levels of containment. So it has to have containment on containment on containment in order to make sure that chemical doesn't get out and destroy the suit and destroy the astronaut in the process. And then any material that could potentially occlude the visor, so not corrode, but just occlude the visor or affect the thermal properties of the suit. So anything can stain or occlude the visor, you have to have 2 levels of containment. So 3 levels for corrosives, 2 levels for occlusives. In space, there's electromagnetic emissions. Stars emit electromagnetic pulses. The sun, that's what a solar flare is a huge EMP, electromagnetic pulse. So excessive radio or excessive EM emissions can damage suits and harm the crews. In fact, a magnetic field that forms at greater than 250 Gauss at the surface of the suit will completely shut down the ventilation system. So if they're out there and this EM pulse hits, or there's an electromagnetic discharge that occurs from anywhere, then that could be absolutely catastrophic because it's going to shut down the ventilation system right away. Even below 250 Gauss, it has the potential to interfere with suit communications, which you absolutely don't want to be out there on an EVA and then have your comms go down, because then there's no way to communicate to get back in. It's going to be very difficult to manage. Now, even if a hazardous chemical doesn't harm the suit itself, so if they're on an EVA and they get exposed to a hazardous chemical while on the EVA, it may not do any harm to the astronaut while they're on the spacewalk or while they're on their EVA, but the problem is that could be brought back into the space station when the astronaut re-enters through the airlock. So, for example, this was a concern with propellants, where if a thruster is fired and the astronaut ideally wouldn't be within range of that thruster, because then that wouldn't be good. But if any like hydrazine or anything were to get on the suit, then they could bring that back in through the airlock, and then you have a hydrazine exposure to the crew that's in the space station. Same thing if they're out and they're fixing an ammonia leak and they get ammonia all over their suit, then they come back in through the airlock. That could introduce it to the crew when they come back in, which would lead to toxicologic issues. The problem is, I already mentioned that if they do get the stuff on them while they're in the EVA environment, it's hard to verify the suit's clean while they're out there. In theory, they can leave the astronaut out there for a longer period for that chemical to degas, to leave the suit, but you can't verify that actually worked. So that becomes a concern of being exposed to something in the vacuum and then coming back and bringing it back in through the airlock. So the best approach overall is just to take all the necessary steps to make sure the astronaut's not going to come in contact with the chemical in the first place. Again, it's easier said than done, but the best way to do this is with the best design controls and chemical controls. And then, every chemical that's used in the space environment has to be evaluated. And we know there's toxic chemicals that are present, ammonia, hydrazine, etc. But anything that has an increased likelihood of exposure needs to be verified. The toxicity of it needs to be verified. And then there's the risk of glass. So some experiments on the space station use glass. There's glass, so this is the cupola, So the observation area of the space station, so there's obviously glass that's in there. If glass were to be broken, it could A, cut the suit, B, the smaller pieces of it could get trapped in the folds of the suit, and then when they come back in through the airlock and they take the suit off, then those glass shards could float out through the atmosphere, and then it becomes a big inhalation risk. And you really don't want to inhale glass shards either. That's not going to be pleasant. Any fragments that are greater than 30 microns pose a risk of cutting the cornea, so it can lead to significant ocular injury. So glass is obviously a huge risk. So the way to minimize the risk of shattering is they have to undergo kick load testing. So it means that any glass that's used in space has to survive a quasi-static load of 125 pounds of force over a tiny circular area of a ½ inch diameter. So a sudden 125 pound force onto a ½ inch diameter area, and it has to survive that and it can't shatter. At the same time, tools can float freely either inside the station or outside of the station if they come untethered. So tools impacting glass also has to be taken into account. So for this, the glass has to survive a concentrated force of 60 pound mass traveling at 1 foot per second on a circular area of 0.08 inches diameter. So again, a very small contact point has to handle 100 or 60 pounds of mass, so that inertial force hitting that very small area. Again, any glass that's used on the space station has to meet these rigorous testing criteria. Thermal extremes I've mentioned a little bit, but contact with, so if you're on an EVA and you touch any hardware that exceeds the maximum or minimum temperatures, could damage the suit, which in turn could kill the astronaut. The biggest risks that astronauts face on a given spacewalk are burn and frostbite. Burns are a little less likely because if you grab onto something that's exceptionally hot, you're going to have pain transmission to let you know how that's hot and you're going to let go of it. Versus if you touch something that's exceptionally cold, then limbs tend to go numb before they experience pain. So frostbite becomes a bigger risk than burn injuries are in a lot of cases. As a result of this, there's been at least one astronaut that's had frostbite for holding on to cold hardware too long. Because there's this risk of burn or more likely frostbite, a thermal evaluation has to be done on every piece of hardware that's used in the EVA environment. So you have to make sure that it's not going to exceed maximum or minimum temperature requirements. So it'll stay within a range, it'll decrease the likelihood of burn or frostbite. Now, inadvertent contact is always a possibility. So we talked about the difficulties of maneuvering in space, the limitations of visibility, reduced tactile sensations. So there's always the risk of inadvertent contact. And so the requirement is that any hardware that could potentially be touched has to remain within a thermal range of -244 to 320 degrees Fahrenheit. So this is just for a very brief inadvertent contact. So it's got a little bit wider temperature range than other equipment does. But it's the responsibility of the equipment manufacturers to make sure these requirements are met. The problem is that some engineers don't think that there's ever a case where their hardware could be impacted or contacted or touched or could ever require EVA access. And so they don't do that thermal evaluation on it, which could be disastrous because, if an astronaut's just translating from point A to point B and they accidentally brush the side of a piece of equipment, again, because of decreased mobility, maneuverability, and decreased vision, then if it's in excess of these temperature thresholds, then it could damage the suit. It could burn the suit really easily. Or again, if the astronaut had to grab it for some reason, it could burn or freeze their limbs. Now for continuous contact, there's another set of temperature requirements. So for inadvertent, there's a pretty wide range. But if hardware or equipment's going to require prolonged contact, so based on 30-minute exposures, they have to stay within a temperature range of minus 80 to 150 degrees Fahrenheit if there's going to be glove-palm contact. So if the astronaut has to reach out and grab something, that equipment has to remain within minus 80 to 150 degrees Fahrenheit. So this range, it won't harm the crew or the suit if they have to hold on to it for 30 minutes at a time. The gloves are going to be thick enough for that. Now, if mission parameters require for long compression of thermal fabric, so if they're in there, they're wedged in against something, it's compressing that thermal fabric. It decreases the distance from their body to the vacuum of space. Basically, it decreases the ability for that suit to distribute heat and cold. It makes the astronaut more susceptible to thermal injury. And so with that, so this is, anywhere else on the body, the temperature range is minus 195 to 240 degrees Fahrenheit. The glove has a lower range of temperature ranges because the gloves are going to be a little bit thinner than the other fabric of the suit is. So that, again, different temperature ranges depending on whether it's inadvertent contact, whether it's glove-palm contact, or whether it's compression of thermal fabric. And then getting towards the end, shock and molten metal are additional dangers that can arise. So the Orlan, the Russian suit, doesn't have inherent shock risk, but the American EMU does. So with the electronics that are out there, there's the potential for shock to occur. It's very low risk, but there is still that risk. Now both suits are still at risk from molten metal formation. So this is generated from if an electrical arc is formed. So they're working on something electrical, so like the solar panels, or they're replacing connectors, they're mating or demating connectors from an electronic thing. If the electricity arcs, it can form molten metal, which can then burn the suit. Then also, if the astronaut gets exceptionally sweaty, which I'll tell you about some mishaps that have happened, is probably they're going to get sweaty. A sweat-soaked interior of their spacesuit decreases skin resistance, so it increases the conductivity of the skin, basically. So any powered equipment that they're using has the potential to cause shock in those cases. So if they made incidental contact with the structure of the ISS and anything that's powered, it could cause enough current to pass through, it could cause 100 milliamps to pass through the astronaut's body, which is more than sufficient to cause cardiac arrest. So anything higher than 100 milliamps can cause cardiac arrest, and it's going to be even an increased risk if the inside of the suit gets sweaty and it decreases that, or increases the conductivity of the skin. So the way around that is you have to make sure that the astronaut is properly grounded, so that electrical current doesn't run through them. It gets grounded out. So recently, as I mentioned, the EVA that was required to work on the ISS solar panels. So obviously these are the big solar panels here. One of them got ripped, and so the astronaut had to go out and fix that as part of the contingency EVA, which would be a very dangerous or a dangerous task in a contingency EVA. It had to be absolutely 100% sure that hazard mitigation was taken care of, so he didn't get shocked when he was out there working on it. The solar panels, they're energized surfaces. If you touch that, you're not appropriately grounded. It can create molten metal, which, again, molten metal is just going to burn right through anything that it touches, so it could pretty much destroy the suit almost immediately. So these are extraordinarily dangerous. You have to make sure that appropriately grounded, and all the steps have been taken to minimize that risk of electrical shock. So the amount of power that's on a connector during either mate or demating operations is the most important determinant of molten metal formation. So any power that's less than 3 amps and 28 volts, it's low enough, it's a low power, low energy situation, so it's not going to form molten metal if there's an electrical arc that happens at that low of a power flow. If a current flow exceeds 3 amps, it will generate molten metal if there's a short. So you have to be very, very careful with those. At sufficiently high voltage and current, so obviously the more current there is, the more molten metal that can be formed if it shorts out. And as the energy increases, it actually generates enough force to kick a person across the room in a 1G environment. So you can imagine if you generated that amount of electrical force and that amount of metal formation in microgravity, it's going to provide a major kick and can dramatically increase the risk of injury. All right, so finish up, talk about a few mishaps that have happened on EVAs, just kind of underscore the danger that goes along with all this. So this one we've talked about in the first lectures, but it's Alexei Leonov and the first ever human spacewalk on Vokshad 2. He got out of the capsule out through his inflatable airlock, and the suit immediately ballooned up, which limited his ability to maneuver. He couldn't physically get back in through the airlock to get back into his capsule. So he had to start letting some air out from his suit so he could get enough flexibility to get back into the capsule. This created a lot of work. It was A, a lot of stress, but B, a lot of physical activity, just trying to, because he kept getting tangled up in his tether, he couldn't maneuver. I mean, again, your ability to maneuver independently while you're free floating in space is negligible at best. And so trying to use the tether to get himself back in, trying to fight and generate enough force to get back in through the airlock, used a lot of energy. Once he finally did get back in, his suit was filled to the knees with sweat, so became very dehydrated, no energy left whatsoever. And then just the problem, he's in microgravity and he's got the suit now that's completely filled with sweat, so making sure that stays contained within the suit and doesn't escape out to the environment. If it escapes into the environment, then there's the potential to drown that's in it, or if it gets up into his helmet. So another hardware failure on STS-121, so Shuttle Mission 121. Astronaut was out on an EVA, and the latches for his safer became detached. So this is the jetpack that they wear out there in case they come untethered from the space station. So this place, or in this case, he was doing EVA outside of the shuttle. But it put the astronaut at a significantly increased risk of drifting away from the shuttle altogether. So they had to cancel the EVA until they could get him back in and get it resecured, and then was able to resume the EVA after that. On Space Station Mission 36, Luca Parmitano's suit, he was out on EVA number 3 of the mission, and an hour into it, started getting all this water that was collecting in his suit, and then he started getting water in his helmet. This is his helmet, so this is all the water that was forming in there. He couldn't complete his to-do list. All this water was floating around. It was getting in his face. He couldn't see anything. The biggest risk, though, was that he was at significantly increased risk of drowning. You inhale some of that water inadvertently in a microgravity environment. You can't really, there's no way to control against it necessarily. So he was at a significantly increased risk of drowning, so they had to immediately terminate the EVA and get him back into the airlock and then figure out what in the world was causing this problem. One thing to keep in mind, though, is that water intrusion is a common occurrence among different EVA mishaps. So whether it's leaking water from their water supply, or if it's sweat, anything else, that's a big problem. They go EVAs. On STS-100, there's an astronaut that had significant eye irritation because of an anti-fog solution, so they polished his visor with anti-fog, because again, that's another big problem that happens on EVAs. The helmet completely fogs over and they can't see, and so something as simple as anti-fog solution gets into his eyes, and then you can't see, and then you can't complete your mission parameters. It increases risk of collision with something on the space station. You can get plumed by a thruster because you can't see that you're floating into it. The list of risks is long. On STS-130, so Shuttle Mission 130 and then ISS Mission 24, and we talked about bringing foreign substances back into the airlock. There were astronauts out trying to fix the heat exchanging loop, which is filled with ammonia. So there was ammonia that was leaking from a quick disconnect fixture, and they're exposed to ammonia. Shuttle Mission 41, the urine containment system in the EMU failed, so there was a lot of discomfort along with this urine floating around, but for that one the EVA wasn't turned. And then Gemini 9, so this was Gene Cernan's EVA. This one almost ended in tragedy. His suit became frayed. It tore along his backside. He had significant heat exposure and suffered significant burns as a result of this. The workload that they put on him, so this is still the very early times of EVAs, and they didn't really know about task management and the energy required to complete an EVA. So they overloaded his to-do list, which made him work too hard, which overloaded the suit's cooling system, so he got overheated. He became exhausted, got dehydrated, no visibility because of visor fogging. The back of his suit started to develop a rip. He got burned. So it was almost a very bad outcome. And then some crew mishaps. Salyut 6, the cosmonaut safety tether wasn't secured to the EVA. He's still connected to Salyut via his umbilical, but he wasn't tethered. So the umbilical, which is providing his life support, doesn't really provide a lot of tethering capability. It wasn't intended to be a tether. And so without being physically tethered, he was at significant risk of floating away from their space station, the Salyut. Gemini 11, astronaut fatigue, caused to be terminated early. And then Apollo 15, tight gloves and repeated action resulted in hand injuries to the crew. So their EVA gloves, again, repetitive action causes a lot of fatigue, and they reported hand injuries. And then there have been a significant number of other missions that reported the same problem. Okay, so that brings us to the end. I won't belabor it. Thank you guys for taking this course. I hope it was somewhat interesting. I appreciate all the feedback that you guys have given me. It's going to help me make it better and better as we go on. It's been a learning experience for me for sure, trying to put all the content together in a way that makes sense. So I've got a lot of ideas moving forward, but thank you guys so much for your participation, for putting up with these lectures, and I hope that it was interesting to you guys. So again, thank you guys, and good luck on finals, and it was a pleasure to be able to teach you guys.